The next topic is binary searching. We can consider the program that we wrote here. We wrote it in order here, so we can assume that the elements of the input array are in this sorted order, and that affects our algorithm. Our existing algorithm works, and it would work if these were out of order, but if they are in order, we know we can stop the search if we ever get to a number larger than our target without finding the target. For example, if we're searching something like this, and we have these values in our array, and we're looking for the target 8, we can stop searching once we hit 9. Because if these are in order, there's not going to be an 8 past this. So our loop is only going to run about 5 times. However, this still is not an optimal solution for the time it would take to run this, since it's practically doing the same thing. It's not really affecting the speed of our loops, especially since if we were to implement this, it would have to run a couple Boolean tests inside of it. Instead, we can use a different binary search algorithm where we can take our two values that are on opposite sides and find the middle of it. And then if our value is higher or lower than this middle value, we're just going to have this middle value, and if let's say it was in this lower range, it would be between 1 and 9, and then we would find the middle of that, which would be 7, and then we would see if it's lower or higher. If it's higher than 7, then it has to be between 7 and 9, so the answer is just 7. But if it's lower, then we're going to have to look between 1 and 7, and then we would just keep going down the line. So if we have this array of type int called numbers, we are going to have these values, and let's say we want to find the value 77. So to do this, we are going to look at our last index, which is 14, and we're going to divide it by 2. That means we're going to get the 7th index. So now we're going to look at our 7th index right here. We get the value of our 7th index, which is 63. We get the value of our last index, which is 98. And we get the value of our first index, which is 11. Now we see if 77 is between either 11 and 63 or 63 and 98. Since it's not between 11 and 63, we can cancel these out. This is the minimum value, this is the mid value, and this is the max value. Now we have only the index 63 through 98. Looking at this again, we're going to have 8 indexes. So we have to find our middle index. That is going to be 82. And we have values on the left and values on the right. Now we still have the value 77. With 63 being our min, 82 being our mid, and 98 being our max, we're going to assume that since it's in order, 77 cannot be past 82. So now it has to be between 63 and 82. From here, our middle value is just 72. And our min value is 63, max is 82. So now we have to find our 77. Well, it cannot be smaller than 72. So this effectively gets canceled out. And now we have our last part where 77 is our mid, 72 is our min, and 82 is our max. 77 is the value we want to find. So that means we have found our value. And it is our min, mid, and max. And it's going to return the index 10. If instead of 77, we wish to find the value 78, all the steps are going to be the exact same. However, we are not going to return a value. We're just going to be left with 77 is our mid, min, and max, which means that there is nothing to return. So in our previous code, we would just return a -1. Now we can write the code for this binary search, or -1 if not found. Before we solve this, we can assume that the array is already sorted. We're going to write our public method. So it's going to be public static. It's going to return type int, and we're going to call it binary search. it's going to take two parameters. First, it's going to take the array, type int, we're going to call it numbers, and it's going to take a target value. Now that we have this, we can write our storage values. We're going to have int min, and we're just going to initialize it to 0. We're going to have int max, and we're going to set it to our max number, which will be at the end of the list, and we can assume that because this list is sorted, this array is sorted. And we're going to do numbers dot length to get the length of the array, and we have to do -1 because there is one more index than there is length, since indexes start at 0 and length starts at 1. Now we're going to have a while loop that is going to find our target value. So this is going to run while min is less than or equal to max. First, we're going to find our middle value, and that's going to be max plus min, and then we're just going to divide that by 2. That 2 should be outside of the parenthesis, so those get added first. And then after we do this, if numbers, and then we want our mid value. If it equals the target, then we're just going to return the target, or we're just going to return the middle value. So we have our mid, and let's say our target is, well, for here, let's just say it's 7. And if max plus min divided by 2 is this index's value, if we put it in our array and we get that value and it's equal to our target value, it's going to just return that, since that would be our answer. Now we need to make an else if statement. If numbers mid is, let's just say, less than target, we're going to execute the following code. We're going to do min, and we're going to set that equal to mid plus 1. What this is doing is it is seeing if our value is less than target. So if we're passed in the target value 10 and our numbers mid is 7, that means we're going to go into our else if statement, and we are going to look at 7 to 56. We know our numbers mid does not equal the target, so instead of keeping mid that number, what we're going to do is we're just going to add 1 to it, so it's going to go 1 up, and that is going to be our new min value. Our last is going to be our else statement, and this is really gonna, it's representing numbers mid is greater than target, and I guess for example purposes we could just do an else if statement. So we have these different else if statements, and if numbers mid is greater than target, what we're going to do is we're going to do max is equal to mid minus 1. And what this is doing is it's seeing if the current mid value is greater than our target. What we're going to do is basically the same thing. We are going to have our max value, like if our current min is 7 and our current max value is 56, that means that our target has to be less than the mid value, which means it's going to be in this range right here. And same thing for the other one, we now have to have a new max value, and instead of making it this max value, it would be this max value, so we would only look at these values. But we know our mid value cannot be the target value because we already have this if statement up here that would have executed if it was. So to minimize redundancy, we would just do a -1 and set our new max to 1 after that. And then, well, and if we go into this while loop again, we're just going to be comparing this part. Lastly, if we don't have a value, we are just going to return a -1. So this is our entire code. This is a super fast way to search. It's much faster than what we did up here previously. Even though there's more code, it compares more values at a time, so it finishes quickly. And we can conclude that this binary search algorithm is in the logarithmic complexity class, or big O log n. The runtime of this binary search algorithm doesn't really differ much between the best and worst cases. In the best case, the algorithm finds its target value in the middle on the first check. In the worst case, the code must perform the full log n comparisons, but since the logarithms are small numbers, log base 2 1 million is roughly 20, the performance is still excellent in the worst case.